Hello everyone, welcome back again. So in this segment, we are actually discussing about logical argument, and we can find out whether a argument is valid or not. So this is the main purpose of our knowing mathematical statement or logical statement. So we are talking about statement or proposition. We know we can evaluate the value of the statement or proposition to either true or false. But whenever someone is having some statement, and someone is making some argument that if this statement is true, I can say that my argument is true. But how we can find out whether is given argument is either true or false? We want to create some valid argument, or given an argument we want to prove that whether the argument is valid or not. So in this segment we are seeing that we are talking about the argument, and we can prove given a argument is valid or not. Okay, so now in our daily life there are actually very simple valid argument that actually regularly arise in our practice. Okay, so these are known as rules of inferences. So there are rules of inferences we are going to show you, and these are very simple valid arguments. Okay, and we'll show you by showing the truth table, or you can use the another theorem using the tautology, and you can see that it is very easy to prove that. Also using some plain English word, they are very uh, easily provable that they are valid arguments. Okay, so one of the rules of inference is known as modus ponens. So in this statement, this is a simple valid statement, looks like this. I am making a hypothesis that if P is true, then Q is true. Now P is true. So I am saying that this is a conditional statement. Okay, it may not be, this is a conditional statement. If P is true, then Q is true. Okay, now P is true. So when P is true, then obviously Q will be true. Q is true. Okay, so if these two is my hypothesis, these two are my premises, then my conclusion B is true. If premises are true, then conclusion will be true, because you can see that if P is true, then Q is true. Now P is true, so obviously Q is true. Okay, so let's find out the simple way to find out whether this is valid or not using truth table. Okay, so here we have simple statement P and Q. We are going to consider all the combinations of P and Q. So we'll find out P implies Q. Okay, so only this will be false and everything else will be true. So then P is true. Okay, P is true, this is our true. So these are our hypotheses. Okay, these are our hypotheses, and if we assume if both of this is true, okay, when we'll assume that this both of this hypothesis is true, we have to find out our conclusion. This is our conclusion, Q is true or not. So you can see that this is the case when both of our hypothesis is true and our conclusion is also true. Okay, so modus ponens is Latin for method of affirming. Okay, we know that if P is true, then Q is true, and P is true. When P is true, then obviously Q is true. Okay, so let's see one example. Say if I am skilled at poker, like a game, okay, any game, let's see, if I am skilled at poker, I will win the game. Okay, so that's one of my hypotheses. If I'm skilled at poker, I will win the game. Okay, so let's say this is my P, I win the game is my Q. Okay, so this is a conditional statement or implication, means if I'm skilled at poker, I will win the game. All right, so let's see, assume this is true. Okay, I mean, we know, let's see, this is true. Now let's see, I am, someone is saying I am skilled at poker. Okay, means P is true. Okay, so this hypothesis is already telling you if you are skilled at poker you are going to win the game. Now you are skilled at poker, which means that Q is true. Okay, it means that you will win the game. Q is true. All right, so this is known for method of affirming. So another rules of inference is modus tollens. So let's see, we have a implication or conditional statement. If P is true, then Q is true. Now Q is not true. Okay, so we can say that P is not true. So let's find out first using the truth table whether we can see that this is a valid argument or not. So we are going to consider all the combination of P and Q. All right, so all the combination of P and Q, will find out P implies Q is true for every case except this case. Okay, then not Q. Okay, and then we are going to find out where both of our assumptions are true. Okay, we can see that this is the case where both of our assumption is true. Okay, so this is the only case where both of our assumption is true, and we can see that our conclusion is also true. Okay, all right, so let's see an example, and let's see an example using English sentence, and we already used that example of couple of times. So let's see, P means this is a dog, and Q stands for this is a mammal. Okay, P implies Q, we know that P implies Q is true. So if this is a dog, obviously this is a mammal. Okay, so this is our hypothesis and this is true. Now let's see, we saw something that's not a mammal. You know that that's not a mammal. Not Q stands for this is not a mammal. Okay, so if you know that some animal, this is not a mammal, you can obviously say that this is not a dog. If this is a dog, that is going to be obviously a mammal. But you found something that's not a mammal. Okay, that's not a mammal. So if this is not a mammal, obviously this is not going to be a dog. So you can say for sure that that could be anything. Okay, but you know that that will not be a mammal. This is not a dog. Okay, whatever this is, you can say that this is not a dog. That's just one way to make a argument that that's not a dog, if you know that that's not a mammal. Okay, so in Latin this known for method of denying. Okay, by knowing that that's not a mammal, you can say that that's not a dog. It can be anything. All right, but you can say that that's not a dog. All right, so another rule of inference is disjunctive syllogism. So here you know that P and Q, P or Q, okay, and not P. So if P or Q is true, that means either P is true or Q is true. Either any one of them is going to be true. Now if P is not true, what does that mean? Q has to be true. Okay, so from the first hypothesis, either P is true or Q is true. At least any one of them has to be true. Okay, now you know that P is not true. That means that Q has to be true. Okay, so let's find the validation. If we draw the truth table, you can see that we are drawing the truth table here. So P or Q is true for every case only when P and Q both are false. Okay, we are finding the truth table for not P. All right, and let's find out the case where both of the hypothesis is true. Okay, so for only this case we can find out both of our hypothesis is true here. Okay, and in this case we can see that our conclusion is also true. All right, so let's see one example. We also saw talked about this example. Let's see one example is that P stands for I am alive. Okay, and Q stands for I am dead. All right, and I am saying either any one of them is true. Obviously I am either dead or alive. Okay, so any one of them has to be always true. So this is the only option. I can be either alive or I can be dead. Okay, now I know that not P, I'm not alive. Okay, not P, I'm not alive. Let's use this example that P stands for I am dead. I don't want to be dead so quick, so that's why I'm just changing this statement. P stands for I am dead and Q stands for I am alive. Okay, so P or Q stands for I am dead or alive. Okay, either any one of them has to be true. Okay, so let's see, I know that I am not dead. Okay, I am not dead, this one is false. I know that I am not dead, so this Q has to be obviously true. That means I am alive. Okay, so obviously this is true that I am alive. So given the hypothesis P or Q and not P, okay, if these two hypothesis is true, all right, if these two arguments or these two hypothesis argument is true, okay, Q will be true. Q will be always true. All right, another rule of inference is chain rule. So if P implies Q and Q implies R, that means P will implies R. Okay, so if P implies Q and Q implies R, then P implies R. So that means if P is true, then Q will be true. That's our one conditional statement. If Q is true, then R will be true. Okay, now that implies that means that our conclusion is if P is true, then R will be true. Okay, so I want to ask you to find the truth table for this argument and find whether this argument, whether you can prove that this argument is valid or not. So I am telling you this is a valid argument. These are rule of inferences, means these are some simple valid arguments we use a lot in our, we are going to use them a lot in our practice. Okay, but I want to ask you to prove that by using truth table. Okay, but let's see one example. Okay, so let's see make some statement. Let's see, P stands for I study biology. Okay, Q stands for okay, so P stands for I like biology and Q stands for I study biology. Okay, and R stands for I pass biology. So P implies Q, means if I like the biology, I will study it. Okay, and Q implies R, means if I study biology, that means I will pass the course. Okay, so if you like the course, you will study it. Now, okay, now Q implies R stands for if you study the course, that means you will pass the course. Okay, so if these both statements are true, if this both argument is true, P implies R will be also true. P implies R is saying that if you like the course, okay, then you will pass the course. So you can see that just by looking at the sentence, you can see that you like the course means you are going to study the course. Okay, now if you study the course, you are going to pass the course. Now let's see another statement. If you like the course, that means you are going to pass the course. Okay, because if you like the course, you are going to study it, and if you study it, you are going to pass it. All right. So here, we are saying that that's another conditional statement. We are saying that another conditional statement will be true. If you really like the course, you are going to study it and you are going to pass that. Okay. So our last rules of inference is known as resolution. So this resolution says that if P or R is true and Q or not R is true, alright, then P or Q is true. So this is our hypothesis, this is our conclusion. So what do we see here? P or R is true. Okay, P or R is true, that means one of them is true. Either P is true or Q R is true. Now Q or not R is also true. Okay, so that means either Q is true or not R is true. That means R is false. Okay, so here if this both argument is true, that stands for P or Q has to be true. That means if P or Q is true, it means that either P is true or Q is true. Any one of them has to be true. And let's see from the hypothesis whether we can prove that. In this statement, it is saying that either P is true or R is true. So let's see P is false. Okay, that means R has to be true. Okay, so P is false and R has to be true. Okay, and here let's see, just we are doing we are assuming that Q is false. So what does that mean? R has to be true, right? Okay, but not R has to be true. If Q is false, then not R has to be true. It means that R has to be false. Okay, but from the first argument hypothesis, we saw that R has to be true if P is false. Okay, so we are assuming that both P and Q is false. Okay, then both this argument is both of the hypothesis is true or not. We are assuming both P and Q is false. Okay, now if for the first hypothesis, if P is false, R has to be true. Now for the second hypothesis, if Q is false, okay, then not R has to be true, means R has to be false. But that contradict this this statement. Okay, that means actually P or Q, any one of them has to be true. Here P or Q, any one of them has to be true. Now if P or Q, any one of is true, then P or Q will be true. All right, so from this hypothesis, if they are true, then P or Q will be true. Okay, so let's you can prove that using truth table. I want to ask you, draw the truth table and find it yourself whether you can prove that. Okay, you can use just simple truth table or you can use the truth table using tautology. Okay, and you can also try to come up with some English sentence. That's how you can prove that this argument is valid. Okay.